Now with a talk on fully randomized pointers by Dhawal, Phaye, Gregory, Roland, Trevor, Carlson from the National University of Singapore. Thank you, Phaye.
Thank you very much, Steve. All right. Good afternoon, everyone. My name is Phaye, and I'll be presenting fully randomized pointers, which is a joint work with my colleagues at National University of Singapore. For decades, memory errors have been the Achilles heel of software written in C and C++. In this talk, I'm going to talk about fully randomized pointers, or FRP, which is a memory error defense that for the first time provides strong capability-like security while remaining compatible with existing unmodified binary software. Let's start with the fundamentals. At its core, memory errors occur when a program tries to access an object or memory outside its intended reference. There are two kinds, I'm sure you're all familiar with: out-of-bounds errors and use-after-free errors. The problem is not new, but these memory errors are incredibly persistent and pervasive. As you can see from industry reports, on the left, Chromium shows that out of the high severity bugs that they patch, about 70% of them are memory bugs, out of which a very significant portion is use-after-free bugs. And on the right, you can see a report from Microsoft Security that shows a staggering 70% of the bugs that they patch have their root causes in memory safety. It's not a small number. They are the primary cause of vulnerabilities being discovered and patched today. And they're not just abstract. These vulnerabilities lead to real-world security disasters that many of us will recognize. From the infamous Heartbleed bug of 2014 that exposed sensitive data across millions of servers due to an out-of-bounds read, to the recent pseudo-heap overflow vulnerability that allowed for local privilege escalation in practically any Linux server that was having the problem. More recent examples show that memory errors pervade in cloud infrastructure as well as the V8 engine that powers our browsers. Each of these incidents was rooted in a fundamental memory error, demonstrating the urgent need for an effective solution. Now, let's look at the anatomy of an exploit. What makes an attacker turn a simple bug into a full-blown exploit? Well, the attacker needs a few capabilities. The first of which is they need to be able to craft invalid pointers, either out of bounds or dangling. They need to be able to dereference these pointers. And they need to leverage the program's memory layout to know where to read or write data or find control structures or put sensitive data. The Heartbleed exploit is a classic example. An attacker sends a malicious request which causes the buffer to allocate more memory than it was intended to, and it reads memory into a buffer, copies it to a response buffer, and sends back to the attacker. It could be passwords, it could be garbled data too, to be honest. However, this is a typical exploit. We have to consider the adversarial strong attacker, a real world attacker, who has all the capabilities that we talked about with one crucial addition: the ability to retry attacks, specifically retry without triggering any interventions. A real-world attacker will not give up. They can try again, perhaps with different inputs. This ability to brute force or systematically search for vulnerabilities fundamentally changes the security landscape, and it challenges many defenses. The power of retry attacks is not just theoretical. Network servers are often configured to maintain high availability, and that's why they restart after a crash, giving an attacker a new attack attempt. Speculative execution attacks in practicality allow invisible number of retries without crashing. And then there is a technique of heap spraying where an attacker creates many objects, hoping that one of them will land on the targeted object. The point is, retrying enables strong attackers to systematically brute force defenses. There have been a certain class of defenses called entropy-based defense that have tried to solve this issue. In entropy, they use randomness. The defense uses randomness. The attacker needs to essentially guess a randomized tag. Incorrect guesses should cause a crash. Pointer tagging uses the upper bits in a pointer, for example, in heap check, to store a tag. Pointer authentication, on the other hand, stores a machine authentication code, a message authentication code, I'm sorry. And then there are techniques such as pointer encryption, which partially encrypt pointer values. The core idea is the same. An attacker needs to guess the random value to forge a valid pointer. And I'm sure it's pretty evident what paths are tagged. However, there's a limitation. The best of these defenses top out at 24 bits of randomness, which is very, very easily bypassed. 24 bits is not strong, not strong enough to stop a determined attacker. To give you an example, a Pacman paper showed that speculative execution is possible to test values at a high rate. At this rate, 16-bit entropy can be brute forced in under 3 minutes. And extrapolating this, 24-bit entropy can be brute forced in under 12 and a half hours. This is well within the means and the capabilities of a patient attacker. Low entropy combined with the power of retries makes a defense practically bypassable. So if this is the limitation, what is the solution? If low entropy is the problem, the solution is much higher entropy. That brings us to our contribution, fully randomized pointers. It's a new pointer encoding to maximize randomization of pointer bits without breaking binary compatibility. To put this in an example, on the left you can see a typical ASLR heap randomized objects, P and Q subsequently allocated. You can see if an attacker has an information about P, they can very well reach Q. On a fully randomized pointer setup, P and Q are essentially large random numbers. Having an information about P does not give an attacker any information about Q, making it impossible to forge. To do this, we had to rethink pointers. Well, what is a pointer? A pointer is just a handle that points to an object in memory. There are a few core requirements that a pointer needs to fulfill. It should support dereference, it should support pointer arithmetic, and it should be packed in a 64-bit machine word. But the core insight is pointers need not be machine addresses. They are just one possible encoding. And most binary software works out of the box without recompilation as long as the core pointer requirements are met. So how do we design an FRP? We start by abstracting a pointer into a pair, a unique object identifier, and a byte offset within the object. For security, we fully randomize these components. When an object is allocated, it's given a new 40-bit ID. We also randomize the offset separately. Finally, we pack this into a 64-bit machine word for compatibility. The result is a pointer that looks like a regular pointer to the program, but is actually a securely randomized abstract handle. On the right, you can see an example. We start with the traditional pointer, which abstracts into the ID offset pair 1, 0. Both components are randomized, and then we pack it into a 64-bit word. However, FRP still needs to allow operations of the core requirements of a pointer. How does FRP do the low-level operations? On the allocation, a new entry is added to a map, which is fairly trivial. We add the ID of the object, base of the object, size of the object, and a packed FRP is returned to the program. Pointer arithmetic is straightforward. We just need to add or adjust the offset part of the pointer. The ID remains unchanged. This preserves object identity across pointer arithmetic operations. As for pointer dereference, when a pointer is dereferenced, the system first looks up an ID in the map. If the ID is missing, we detect use after free. Then we perform a bounds check. And if any out of bounds accesses are caught, we raise an error. If both of these checks pass, only then do we allow the dereference to proceed as normally. On the right, you can see an example. The top is an example of a map entry. Then we are performing a pointer arithmetic operation, which is taking forward as it should in a regular program. The BlueFat part shows the interception of our technique, which decodes into the base address, and finally does a bounce check. After passing, a traditional dereference takes place. This approach ensures that every pointer operation is both compatible and protected with minimal disruption to the program logic. Now let's see what is the security impact of such a technique. We achieve a baseline security of 52 bits of entropy, which is an astronomical leap from the 24 bits in prior approaches. The high entropy provides robust protection against both use after free and out of bounds errors. An attacker would need to guess a 52-bit random value to attack a pointer Q, having an information about P. Just how hard is it to brute force 52 bits? Let's put it into perspective using the examples that we saw before. For the network server reset example, 52 bits of entropy, an attacker would require 2 to the 51 guesses for one attack. The TCP handshake traffic itself would exceed 240 petabytes, making it intractable. For the speculative execution attack, using the same optimistic rate, for an FRP space, it will take 384,000 years, which is far exceeding the 24-bit defense. Even a massive heap spray that allocates billions of objects barely makes a dent. The FRP space is so vastly larger than physical memory that the probability of a successful attack is negligible. With 52 bits of entropy, brute force attacks are no longer a viable threat. To prove the practicality of our design, we built 2 prototypes. BlueFat, which is a software prototype built on Intel Pin Dynamic Binary Instrumentation Framework that is used to test security and compatibility. We also developed GreenFat, which is a hardware simulation built on the Gem5 simulator. The purpose was to evaluate performance. Looking at BlueFat, our security evaluation shows that FRP prevails where others fail. On the right, you can see a table. The top represents CVEs ranging from weak to strong, including the strong attacker model that we discussed before, with the ability to write retry attacks. We tested a bunch of defenses on them, and you can see FRP is the only one that's completely bypass safe or doesn't fail in the attacks. Even more importantly, BlueFat successfully runs the entire Spec 2017 suite, which comprises of C, C++, and even Fortran binaries without any recompilation. This validates our core hypothesis that FRP's novel pointer encoding is highly compatible with real-world off-the-shelf binary software. Well, security and compatibility are good, but not at the cost of performance overheads. This is where GreenFat comes in. We simulated a hardware-accelerated design and added a small dedicated GreenFat cache to the processor core. This cache stores FRP to address mappings, and we decode translations on the fly. This only adds a cache hit latency of 2 cycles. The results are excellent. We get less than 4% geomean performance overhead when testing on Spec CPU 2006. This is well within the acceptable range for an always-on security feature in production systems. In conclusion, we have shown that it is possible to fundamentally redefine pointers away from machine addresses to achieve a new level of security. Fully randomized pointers offer 3 benefits: an unprecedented baseline 52-bit entropy with high binary compatibility and practical performance overheads for production systems. FRP demonstrates a new superior trade-off point that strong bypass safety and binary compatibility can coexist together. We have open sourced BlueFat on GitHub for you to explore. And for more details, you can check out the paper. Thank you for your attention. I'd be happy to take any questions.
Thanks for the great talk. Yes.
Thanks, very nice work. People often do things with pointers that are kind of outside the C spec. So some things, we work with Cherry, which is kind of similar to what you do. And some things I think you can support that we don't. So sometimes people hide pointers just by knotting the bit pattern. And I think that would work with your thing perhaps, wouldn't it? Sorry, rest of the question. And other times people XOR pointers. And I don't think that would work with your thing, would it?
You're right about some techniques that use, for example, NAND boxing in Chrome or SpiderMonkey, or where the pointer bits are otherwise used, will be incompatible with FRP. But that represents a small part of the software stack as well, in terms of compatibility, right?
Martin Mask, Google DeepMind. Really nice talk. Really enjoyed the work. Building on that question. So there's some of the uses of these high bits are, for example, for distinguishing kernel pointers from user mode pointers. And then, of course, there's also canonical addresses versus malformed addresses. And so it seems like currently this is assuming all of that is randomized. But could you imagine extending your work so that it becomes configurable? So, for example, that you could require all of the random addresses to be canonical addresses?
Well, that is a good direction to think about. Even in our example, the ID and offset parts, as you saw, they are configurable. You can change the part that stores the ID as well as the part that stores the offset. This is practically done to avoid large objects, which currently only supports, you understand, only the 6 down bits, bottom bits. We can extend that to be a configurable system. This is just the baseline example, but yeah, that's a good direction I can think about.
Thank you. So, on the same topic at the end, how are you distinguishing which part's offset and which part's ID? Like, is that variable or is it fixed? And does that limit the number of objects and the size of objects?
You can configure before the start or before the running of before you run the program. So it's static once you start it. So you can decide how many bits will represent offset or how many bits will represent ID, but it's not variable while running the program for sure.
Have you considered encoding a size class in there to give you a variety of splits between offset and base?
We have not, but thank you for the feedback.
One more question.
So some programming languages, including C, can use garbage collected system, and some garbage collection algorithm will have this kind of operation. They will linearly scan through a range of memory and go from address one by one and find places where existing object is allocated. But because if pointers are randomized, is it still possible to do this kind of linear scanning? Thank you.
I mean, it could be possible, but then GC would have to not pass through the randomized setup, because as we see, the memory layout is not randomized. The memory is still getting allocated contiguously. It's only the abstract handle on the virtual side of it that is getting randomized. So GC can work with physical addresses. Maybe that's a solution.
All right, let's thank the speaker.
Thank you very much.